You're probably wondering, how I was able to make this from just this? Well, I've got good news and bad news. The good news is it's fairly straightforward. The bad news is you're gonna need a little more patience. Just 8 minutes longer. So buckle up, boys. This might get hairy. But first, let's go back to the beginning. To understand how such thing is even possible, we need to know what the hell struct really are. A struct as you know it is kinda big goddamn lie. In memory, it's just a buffer. In this example, the entity contains 3 floats for the position, 1 float for the speed, and 1 boolean, which is 17 byte. Because a struct must align to the largest type, in this case a float, which is 4 byte, the compiler adds 3 bytes of padding, and this is why it's not a good idea to add a boolean to struct like this. We store the struct metadata in this table, and I'm gonna to include even more, because why not? This represents all the metadata we need about the struct. Right now, we can define the entity like this, and access it like this. However, this way of accessing the struct will always be manual. Since we've collected a lot of information about the struct itself, we can now access it in much more interesting way. In this example, I can take the instance of the entity struct and cast it to 8 byte buffer, so we can operate on it on the byte level like this. We know from the table that the first field is located at offset 0, and it's float 3, so we cast it to float 3 pointer, then dereference it to get the actual value, and assign it to new variable called position. Doing the same for the other field as well, we can print these values, and we will get the exact same result as if we access it normally. Now you might ask, what if the struct has a private property? Well, it's fucking useless, and you can still access them, which is great. The entity struct, as you can see, contain multiple fields. Each field can be described by its type name, size, and offset. A type is simply a collection of fields, so we describe it using type name, size, the offset of the first field, and the field count. You'll see later how the offset and the count fit into larger collection of fields. Finally, we have a registry that we can use to access all of this data. In each project, we can generate this data so we can query it later at runtime. We define the registry to point to the fields and types, and we access it using helper functions under the meta and the project namespace, as you can see in this example. Right now, the data exists only for the entity type. If we add another type, we can store the metadata in exactly the same way. The entity type starts at offset 0 and has 3 fields. The camera type starts at offset 3 and has 2 fields. Assuming the data is already generated and ready to use, we can begin adding helper functions that makes easy to access the registry, query types, read the field value, and even more interesting things like iterating over the fields of given type. This will be extremely useful later on. To use the system, we need a set of helper functions to access the registry and types, either through template parameter or simply by name. I'm gonna to move these functions under the project namespace to make it look like reflection for the project. This represents the Meta API we need for now, but this starts to look like boilerplate that we have to write manually for each project. So I wrap it up in a small macro. I'm going to call it meta header. I'm going to place all the meta related code under my core header, and I move the types under the project namespace just to be consistent with the Meta API. Now we have a problem. How the hell are we going to generate the metadata? Well, I can take the header file and feed it into a new program. I'm going to call it meta. Of course, most projects don't have just single header file, so instead of passing one file, we pass the entire source directory. The meta program scans that directory and find all the headers and include them all into a single CPP file. At this point, we're ready to parse that file and extract the metadata we need, but there is no way I'm going to parse C++ code by myself. Fortunately, we can use one of the tools in LLVM project called libclang. LLVM is a huge repository that contains many compiler tools. In our case, we only interested in libclang because it gives us access to the C++ AST or abstract syntax tree, which is basically your C++ code but as tree. Using the library, we can access the AST and do a little bit of processing to generate the metadata. This program can be hooked into pre-built step of the build system. I'm using Premake to generate MS-built files, so the setups look like this. But what if using CMake? Well, God help us all. Back to the sandbox example, I hook up the meta program and hit build. As you can see, there is an explosion of meta types. Because I included a lot of stuff in my core library, I probably have to do something about it at some point. To solve this issue, I explicitly add a notation to each type and property. This annotation is just a macro that wrap Clang style annotation and expand to nothing on MSVC. I then modify the meta program to only include what actually annotated. Let's build again. And there it is. Right now, I'm only printing the metadata, but if I switch to generation mode and build the project, the metadata will be written into CPP file, which is great. By the way, the metaprogram code is really trivial to write, so I'm gonna skip over it. Now that everything is set up, we can start to write the function that generates UI from struct. To make it work with any type, we turn it into template function. Using the meta API we wrote earlier, we can access the project namespace, in this case sandbox, retrieving the type information, check the type, and write the UI layout. Next, we iterate over the fields and handle each one based on its type. For now, I'm only going to handle floats and booleans, since I need to fit the function on the screen. Finally, we can place this under I'm going namespace or wherever it makes sense. Now, let's try to build the program. And it's working as expected. Right now, I'm using string comparisons for each type. It works, but we can do better. I'm going to define set of comment types as enum and generate this enum value as part of each field metadata. Then we can transform this if-else chain into simple switch statement. This is pretty much everything you need to build a simple reflection system, but I'm going to add one more cool feature. When we annotate the type, it's often useful to attach extra metadata to it. For example, in the entity struct, we could mark the position with a color, speed as a slider with a range, and enable as a text. To implement this feature, I define a bunch of attributes like UI, color, and range. Then, I wrote attribute variant using union and enum. On each field, I add an after and count that reference a large array of attributes, which is look like this. Using this, we can upgrade the struct function to handle the attributes. Let's build and run the program. We can see the color, the slider with the range, and the text. Now, you might ask yourself, is this useful for anything else? The answer is absolutely yes. Assuming we need to serialize the entity and camera types, we can automate that using this tiny JSON serializer. It works exactly like the UI function. We loop over the fields and handle each one individually. Then we can use it just like this. And here it's working with the serializer. The UI and serialization systems shown here are the simplest possible versions I could fit into YouTube video. And they can definitely be extended because the core idea is that simple. That's how simple reflection system can be built in C++. Thanks for watching and see you next time.